Okay, so let's start. So let's just recap where we were without reproducing all the intermediate steps because we drew the diagrams that we drew, and I need to fix some notational issues. So we're still working with our 5-4 theory. Genetic term minus the potential, which is, as the name suggests, a quartic potential. And what we set out to do was to figure out how to calculate the endpoint functions. And in fact, we know now what to do, right? So in particular, in the fully nonlinear vacuum, what we discovered was that there's a prescription in terms of Feynman diagrams. So one thing I want to introduce is this common notation, which is that if you have a 2-point function, so you have two external points, but because you're trying to do perturbation theory, you kind of just draw a log, and you represent this to mean just a sum of all the fully contracted Feynman diagrams. That's what that means. And in particular, what we've discovered was that, for example, the first two diagrams is, the first guy is a classical guy, semi-classical, maybe I should say that. And then from the 5-4 interaction, this is the order lambda to the 0th diagram. This is the order lambda to the first diagram. And furthermore, what we did was to actually go on to Fourier space. Okay, and so let me just write down without going through the all the intermediate steps. So what we did instead was to so actually this is where I want to fix my notation. So if we go to Fourier space, of course, blah blah blah, there's an infinite series. And as I said before, the 2-point function, just like the classical, in the subclassical case, we view that as the classical, it describes how the classical, semi-classical propagation of the particles themselves. And so you should view the higher terms as the quantum corrections to the propagation properties. And so people even study this in curved space-time, as I briefly mentioned. For example, even QED, quantum electrodynamics in curved space-time, is still an ongoing topic that people look at. So what we did was we went to Fourier space, really Fourier space-time, and that's where I draw a line, because now, instead of having x and x prime as external points, now we have external momentum, because we have the Fourier transform this guy and this guy. Of course, because it's a 2-point function, remember, what's going to happen is there's always going to be a momentum conservation. But just to prepare us for the higher point functions, let me just draw it in this way. So I have incoming K1, and then I have an incoming K2. And if both are incoming, then they must sum to 0 by momentum conservation. So there's always an overall momentum delta function. If I'm in G space-time dimension, there's always going to be this. So that's why we drop it. So we're always so this is always proportional to this. So likewise, just like this guy, I mean, the diagram is the same, but we are going to, again, Fourier transform this guy, Fourier transform this guy, and so on. And so let me just go ahead and tell you what we actually end up writing. Right? So this guy is really just, let me call it, let me stick to this convention, K1, K2, but really it's just I over K1 squared minus M squared plus I epsilon. Okay, and of course you can write that as K2 as well. But like I said, usually we just omit the delta function because if you want the Fourier space answer, that's what the content of this diagram really is about. And then likewise, there is a momentum counterpart to this, and we have P going inside. And P is not constrained because P going out plus P going in is 0. So there's no constraint here. So there's always there's a I over P squared minus M squared plus I epsilon. And then there's an interaction here. And here we will discover that there is in fact a minus I lambda because of this guy. There is some momentum conservation, but you will integrate over it and you will discover that that's just going to give you the momentum conservation. But now there's an integral over P. Okay? So there's now an integral over P. So let me write that down. P over 2 pi to the d. And then the rest of the factors will be K1, K2. It would just be basically I over K1 squared minus M squared plus I epsilon whole thing squared. Okay? And higher order terms. Right. And so this is plus. Okay. So leave it as so this corresponds to this. This corresponds to that, and let's move on to the 4-point function. Right. So as I mentioned before, the 3-point will never be, at least within perturbation theory, it will never be non-zero. It will always be 0 because of the structure of our theory. Right? There's always a 4. There's always going to be even powers of the non-linear term. Yeah. There's always an even power of fields in our non-linear term. And so if you have an odd number of external fields, then the total number of fields, when you expand it out in perturbation theory, is always going to be odd if the external fields are odd. So that, by Wick's theorem, tells you that the answer is 0. I'm not sure whether in the non-perturbative sense, whether it's possible to get a non-zero answer. If anyone knows the answer, let me know. But sometimes funny things like that happen. So some things that look 0 in perturbation theory ends up being non-zero somehow. Meaning there are things that are missed in perturbation theory that cannot be captured unless you somehow find a way to go beyond that and find some non-perturbative, maybe not the full answer, but some aspect of the full answer in the non-perturbative regime. So, for example, there are results in quantum field theory that goes like 1 exponential of minus 1 over the coupling constant, G. G is like lambda, let me put it as lambda. There are results that go like that. So this is you can see that this is non-perturbative in lambda, right? If you try to expand this in around lambda equals 0 doesn't quite make sense. Okay, this doesn't quite make sense. So how do you get that from summing over Feynman diagrams? I don't know. I think it's not, in fact, probably not possible. Right? So things like that happen, and so that's why I mentioned this problem. But anyway, at least in in perturbation theory, odd powers of fields don't matter. Okay, so the 4-point case, now again, we will denote it as, now instead of x1, x and x prime, maybe I really should have called it x1, x2. Anyway, x1, x2, x3, x4. Again, you draw a blob. Again, to denote that this blob is just notation for saying you're trying to sum up an infinite series of diagrams, and it's just to denote that unknown. It's really unknown. Nobody knows how to do this to all orders. And I also have mentioned this before. Even if you can do it to all orders, you still need to find a way to kind of massage that answer to get something sensible. The sum of the series in powers of lambda will eventually give you a divergent answer. Right? The higher powers you go, you will hit a point where, for a fixed value of lambda, will not converge. The radius of convergence is usually 0. Anyway, so what is this guy? We have seen it goes like this. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then with so these guys are order rounded to 0, and then I'm just going to stop at the first classical. This is order lambda to the first power, okay, and so on. Okay. And so in Fourier space time, again, so that I can fix my slight problem with my notation, which is so that I can emphasize particularly the momentum case. So now I can say this is incoming K1, K2, K3, K4, and this is again is supposed to mean that I take this answer and I Fourier transform x1, x2, x3, x4 into K1 through K4. And so again, I'm going to leave out the delta functions and what I'm going to write. But remember, all of these guys are necessarily, because our background is flat space-time, all of these diagrams, if you keep track of all your delta functions, will always have an overall momentum conserving delta function. Okay, and so let me just go ahead and write down these guys without those delta functions. So this is equals to this guy is just remember it's K1 coming in, K2 coming in now, K3, K4. Okay, and again, actually there are now two delta functions. One for K1 plus K2 is 0. One for K3 plus K4 equals to 0. But again, I'm just going to say that this is K1 squared minus m squared plus I epsilon times I over K3 squared minus m squared plus I epsilon. Okay, of course I can write k4 or k1, but there is a delta function. Right? Maybe in this case I should write it down. So there's a delta function of k2 plus k1, and then delta function of k3 plus k4. And then I'm not going to write down all the permutations. I'm just going to say permutations plus two permutations, right? This guy and this guy. But it's just a swapping of your momentum, basically. And what's non-trivial is the next term, which is this guy. So this is now k1, k2, k3, k4. Okay. But again, after you throw out the overall delta function, okay, maybe to stay consistent with this guy, I must also say this is actually k1 plus k2 plus k3 plus k4. But the main point here is that the vertex corresponds to, after you do all your integration, right? Each vertex, remember, originally contains an integral over space-time involving this guy, the fourth power of 5. But after your contractions and so on, you will discover that you're left with minus I lambda. Right? So this is the Feynman rule for this vertex in momentum space. And then just multiply by all the external propagators, k1 squared plus minus m squared. Let me write it in a more compact form. It's just the product of I over kl squared minus m squared plus I epsilon. Okay. Times the delta function. All these delta functions will, when you calculate amplitudes, will all turn out to be irrelevant. Even this diagram will be irrelevant. But so yes, so that brings us to, so this is just recap. But it allows me to fix my notation to emphasize that when there are n points, there are always n, in principle, always n incoming momentum. But of course, sometimes like this diagram, there are momentum conserving delta functions. So you can exchange, sometimes you can exchange one momentum for the other. But what's going to happen is that we are going to now ask the question, what do these guys tell us about physical observables? Right? So this is where we kind of become high energy physicists and ask what can we extract from this? And the answer is that this endpoint function calculations, one of the key applications is to allow us to extract the amplitude for particle scatterings. Right? So what you should think about is the following. So I think I have to erase something. Because I have to. Okay, so let me erase this part. The position space time. The position space will turn out to be not so relevant because usually we are scattering particles with a sharp, fairly well-defined incoming momentum. Okay, yeah, so let me leave these two sections intact. Although this 2 point is also not so critical. So so the endpoint function allows us to extract the scattering matrix, the scattering amplitude. And so what do we have? What do we have here? So what you should think about is that you should let's try to collide. Yeah, let's do this. So we have m incoming particles, which I'm going to label as I call it incoming order K's, and then just a second. All the outgoing I call P's. Okay, so K1 all the way to Km. Some stuff is going on here, and because we're doing quantum field theory, we are not obliged to preserve the number of particles. In other words, if you have any incoming particles, depending on the type of interactions allowed in your theory, you do not need to preserve n outgoing. So we are allowed to have, for example, n outgoing particles. So in our theory right now, phi 4, we are only dealing with phi particles. So obviously, the incoming and outgoing particles have all better be phi particles. But later on, when we do quantum electrodynamics, then things do change. In fact, we can have electrons converting into muons. We can have production of photons. So electrons can generate photons. Photons can generate electrons, and so on. And so the species of particles can in fact change because of the interactions. That's in fact the many-body or variable body aspect of quantum field theory that I try to emphasize at the beginning of this course. Right? So one of the key reasons why we do QFT is because the number of particles, the system that you're looking at, so to speak, if you think of a particle as a quantum system, the system itself can change from one particle type to another particle type. And so the paradigm for high energy physicists is in fact the scattering experiment, where you shoot particles at each other, and the LHC is mainly the protons at CERN, not CERN, SMAC in Stanford. I think it's still the frontier of electron colliders. At SMAC, they collide electrons, electron positrons, I think also. And so there's some discussion, for example, of this constructing muon colliders as well. Anyway, so depending on what you collide, you will be able to generate particles, new particles, right? And of course, different collisions will preferentially generate different types of particles. that is why we want to be able to predict what is the probability that you will generate, for example, muons when you collide electrons together. What's the probability that you will generate quarks? You won't see free quarks in nature, but downstate of quarks, hadrons. What's the probability that you get a pion when you collide protons together, and so on, right? So this is basically the main idea. So the way we think about the way we denote this is that usually we call this the S matrix. So the amplitude for this process is given by this symbol. So I have K1 through Km incoming, and then through some time evolution, meaning that through the interactions of the particles, you will get out n particles, P1 through Pn. And that's, by the way, why we start with scalars, because there are no other labels around. Later on, when we do fermions, there will be a spin label. When you do photons, there's also a spin label. It tells you basically what the polarization would be of your photon or your electric field, so to speak. And so the square of this will, in principle, tell you the probability, right? And so how do you calculate this? That's the question. And that comes back to what we were doing previously. So it turns out that this guy is related to the n plus n point function. And this is through what's called the LSZ reduction formula. Okay, so to remember to re-record this. Okay, so yeah, so let me just say in words first. So this can be extracted from the n plus m point function in momentum space. I should really call momentum space time, right? But anyway, momentum space and Fourier space, I use this phrase interchangeably. And so how do you exactly do it? Let me just do it symbolically first. So what you do is you look at the diagrammatic level. For example, most of what we're going to do, in fact, I think all of what we're going to do is we're always going to have two incoming particles, and then we will ask what happens. Okay. In fact, usually we just do 2 to 2. That's, as you will see, is complicated enough. The amplitude calculation is oftentimes complicated enough. And so what happens? So let's do 2 to 2 scattering. Okay, 2 to 2 scattering. And so what's going to happen is that in general, this guy itself can be split into the diagrams for the 4-point function. This is the 4-point function. Can be further split into the following. Okay, so there's a central part of the diagram involving all the complicated non-linearities and so on. But there will always be, remember that, for example, look at this guy. There will always be these external range functions, but they themselves will be corrected by quantum corrections. Right? So there will be bubbles and loops and so on. So this can be further split into the following. Okay, so the full point itself, the full 4-point itself are these quantum corrected Green's functions contracted with the chord diagram, which involves all these complicated non-linearities. And it turns out that it is this part, that gives you the scattering amplitude. Okay, that's what I want to do schematically first. There are some subtleties regarding what exactly this means. It's actually the pole. You're going to extract the part that is nearly on shell, which means that it's basically because these are real particles, real outgoing particles, right? So they all satisfy the dispersion relation, k squared equals m squared. So when you do that, the Green's functions here are not the full Green's functions, not the full quantum Green's functions, but near the poles. But in any case, for our purposes, we just need to focus on throwing out these external guys, the external Green's functions, and focusing on this aspect. So what does that mean? For example, let's look at the 2-to-2 scattering for our 5-4 theory. So for our 5-4 theory, these guys are exactly these guys I'm referring to, right? And because we're not even doing any classical quantum corrections just yet, the quantum corrections will involve, for example, maybe a loop like that, and then there'll be permutations, and so forth. You can even have two loops, one loop here, you can have another loop here, and so on. So it gets increasingly complicated, but all of that is not relevant, as I'm trying to emphasize here. And particularly what we see is that for the 5-4 theory, once you throw away the external propagators, which are these guys here, then actually this term for 5-4 theory, that tells us we have actually successfully calculated our first scattering amplitude. Right? So in fact, the non-trivial part, the non-trivial part of 2-to-2, 2-5 scattering is actually just minus I lambda. So we'll write the following. I'll write scattering amplitude 2-to-2. Let me use my notation here. K1, K2 to P1, P2 is equals to minus I lambda. And then usually there will be a delta function. So I will write this, but we'll factor it out. So K1 plus K2, and then minus P1 minus P2. Because now I've reversed the direction of the momentum. Right? So all the ingoing is plus, but if I have two of them going out, then it will be minus P1 minus P2. And then what usually we do is we define the delta function. We define the scattering amplitude itself with this delta function multiplied with K1 plus K2 minus P1 minus P2. So that the X and then plus higher order corrections. So therefore, the amplitude itself is just this simple answer, minus I lambda. Okay, we even put in the I. I want to emphasize this word, non-trivial. Okay. Why do I say that? Because actually, you might have noticed I ignored these terms. So the reason why this is called non-trivial is because these terms actually tell you basically nothing about the interactions of this theory. What this tells you is that K1 will go to K2, and then K3 will go to K4, and then you have permutations. What is this actually? This is just telling you that nothing happens, right? The particle comes in, and just keeps moving. It doesn't do anything. And then why are there permutations? There are permutations because of both statistics. Right? So if you shoot two particles of the same type in an experiment, there's no way to distinguish between the two of them. They are bosonic particles. So that's why you necessarily have to interchange permute order rather than momentum, because you can't distinguish between, is that really the K1 particle or is that really the K2 particle? You can't tell them apart, right? Electrons, for example, are indistinguishable, but they are fermions, so we'll get to that. Photons are indistinguishable, but they are bosons. They have a spin, but in that sense, they are similar to the situation here, which is that under interchange, you can't tell apart, is that the K1 photon or is that the K2 photon, right? If they're all indistinguishable. So that's what's happening over here. But otherwise, there's no interactions whatsoever. No interactions. But this is the first order in interactions. So I kind of jumped to the non-trivial answer right away because that's what's important. But that's what we're trying to go after when we do an experiment, right? You don't scatter particles just to watch them go straight on. You scatter particles so that you want to extract the part that actually tells you something about how they interact. And so this, in fact, is how to calculate it. I should also mention that this guy S, because of this distinction between interactions and the no interaction part and the interaction part, is often split into the identity, which is actually the no interaction part, plus I times T. So people usually call it S matrix, but it should really be called the T matrix, because the T matrix is the part that contains the interactions, right? So that's really what we're calculating. And so, I should write it somewhere. Let me do it over here. Yeah, so usually we don't scatter one particle of nothing, right? So we don't talk about this. But what this does tell us, as I said already, it tells us something about the propagation properties. So that's why we need the 4-point calculation. So let me just say this. So with that definition, then the amplitude for the n particle going to m particles, the other way around, n particles going to the n particle calculation, usually we would define it with the delta function factored out, Km minus P1 minus P2 all the way to P minus Pn. This is in fact the T matrix I, and then the incoming K's, so K1 through Km, T matrix, and then P1 through Pn. And then sometimes there are spin labels, and sometimes other labels. For example, you can have color, you have group theory labels, and so on. Right? But let's not get so fancy just yet. Right? That it will get slightly more fancy once we do QED, but we won't do non-abelian gauge theory. Any questions at this point? So, So what we're going to do is we're going to, so you've seen this very simple example. So what we're going to do is, with this understanding, we're actually going to now move on to do more complicated theories, as I've alluded to, because ultimately what we want to understand is some real-world phenomenon, right? Some basic processes in real-world phenomenon. So 5-4 theory is, as far as particle physics is concerned, not really real-world, right? But it is the place we learn kind of the basic tools, basic scheme of QFT. But now we should actually move on to do some spinors and photons. So our goal is the following. So for the next an hour or so, I'm going to go back to kind of redo some of these endpoint function calculations in the non-interacting case, just to remind ourselves, right? So what have we done here? We have done we have figured out how to calculate the non-interacting endpoint for the scalar field, right? And then what we have done is we have used this to build perturbation theory for this guy, for the interacting scalar endpoint function. So these guys are the non-interacting vacuum. These guys are the interacting vacuum. And then we have, from here, just figured out that when you throw out the external Green functions, what remains minus these trivial interactions, no interaction, trivial diagrams involving no interactions. Once you throw this out, then what remains is the actual T matrix, right? And that gives you the non-trivial part of the amplitude. So that's going to be our strategy. We're going to do this for photons, and we're going to do this for fermions. Actually, I think I'm going to do fermions first, and then I'm going to do photons, because fermions require some discussion of this Fermi statistics. So that's going to be our program for the next week or so, I think. And then hopefully by the end of the remaining part of December, we can, what I'm looking for this great here it is. We'll be actually calculating some actual processes. Let me start from here. So the derivation of this actually is quite involved, which is why, as you notice, I'm skipping it, because even in Pesky and Schroeder, for example, it took them until chapter 7 to actually work this out. The full answer is quite involved and I think quite difficult to understand for the first pass in QFT. So I'm just going to tell you that's the prescription, right? So I do it for 2-to-2 scattering, but I hope it's clear. It works for any number of incoming and any number of outgoing, right? Just look at your n plus m point function, throw out the external quantum corrected Green functions, nearly on shell guys, and then just extract the core of the diagram. And once you've done that, actually, you can put every particle on shell, right? All of them, you can use k squared equals to m squared in your final amplitude, final answer, because they're all real particles now. Good. Okay, so let's now do fermion. So we're going to begin, like I said, with the non-interacting case. And so the non-interacting case we've discovered is described by the Dirac equation, which I'm going to introduce a slightly new notation. This is the Dirac equation, as you remember. The first part of our course is I'm assuming that people are not familiar with the Dirac equation, which actually spans understanding the valence group, and which then slowly build up to the Dirac equation. As you remember that in 4 dimensions, there's an intimate relation between SL2C and the valence group. And SL2C had two kind of left-handed and right-handed representation. And in fact, by combining them through making sure that our resulting equation is in fact parity invariant, we discovered the Dirac equation. So that's not quite how Dirac discovered this equation, but that's how I think in 4 dimensions at least, that's the more modern approach to understanding why the wave equations are the way they are. Meaning you want them to transform covariantly under the appropriate space-time Lorentz transformations, and in this case, including parity and time reversal. So unfortunately, we ran out of time to talk about time reversal. Ran out of time to talk about time reversal. Okay. Anyway, so but that's where we were. So I should explain. So this slash notation is due to Feynman, as I understand the history. But this is actually simply the contraction of our gamma matrices with the partial derivatives. And the gamma matrices themselves, as you remember, we built them out of Pauli matrices. So sigma bar mu, sigma mu, and these are off diagonal terms, and these are all 0. So this is 2 by 2. The Pauli matrices are all 2 by 2. So therefore, the whole thing is actually 4 by 4. Okay. And so what the key property is here, obeyed by the gamma matrices, are that they actually obey anti-commutation relations. So sometimes in some books they write this anti-commutation as bracket with a plus. Sometimes people write it this way. But in any case, what this means is it's gamma nu plus gamma nu, gamma mu. Okay? This, as opposed to just commutation. Commutation is a minus, anti-commutation is a plus. And this turns out to be 2 times the metric, eta mu nu. Okay, so this formula is called the Clifford algebra. And how would you generalize, for example, the Dirac equations to different dimensions? That's how you start, in fact. You first start by finding a set of matrices that satisfy the Clifford algebra. And so I won't go into the details, but you can use then, once you have done that, then you can use them to basically construct the same form of the Dirac matrices, Dirac equation. But now the matrices are no longer necessarily 4 by 4 anymore, right? It just depends. So for example, in 2 dimensions, one time and one space, the Dirac matrices, the gamma matrices are 2 by 2, and in fact they just turn out to be related to the Pauli matrices themselves. So I think one of the homework problems, which I'm going to put out very soon, is going to be verifying that Pauli, a certain subset of the Pauli matrices are in fact the gamma matrices for 1+1 dimensional fermions. So that's how you go. Once you have found them, then you can use these guys to construct the corresponding Dirac equation in different dimensions. So yes, you can do fermions in dimensions other than 4. But let's focus on this for the moment. So what we want to first ask is, how do you get this out of the Lagrangian? Because we want to quantize this. It's now trying to quantize these the Dirac equation, right? And so how do you do it? You, in fact, it's not difficult. So I claim that the Lagrangian is just given by something called psi bar, which I'll explain in a little bit, times basically the left-hand side of the Dirac equation. Okay. So how do you see that this is true? It turns out that you can argue that so you notice. So firstly, you notice that this is the first order Lagrangian, and so and then secondly, you can think of this Lagrangian as a function of psi and psi dagger. Okay, because psi is complex. So what you can think about is that this equation is linear. So you might think about, that's one way to think about. So you can split it up into the real and the imaginary parts. And you can ask, okay, if I vary the real part independently of the imaginary part, I should be able to get from the Lagrangian the real part of the Dirac equation, right? It's supposed to satisfy a variational principle. Then when I vary the real part, I should get the real part of the Dirac equation, and when I vary the imaginary part, I should get the imaginary part of the Dirac equation. So, or I can think about just simply treating the psi and its complex adjoint. Actually, I should call it the adjoint, not because it's a four-component object. X independent variables, right? So saying that X and Y in a complex combination, X and Y are independent, is the same as saying treating both the X plus IY and X minus IY as independent, right? So this is independent variables. It's the same as saying X, Y are independent. Okay? Because here you have two variables, here you also have two variables. So that's the quickest way to see that, in fact, you get a Dirac equation. So how do you see it? Well, the Euler-Lagrange equations, remember, are the following. You get partial mu d mu psi dagger equals to dl d psi dagger. That's the Euler-Lagrange for psi dagger. You can do it for psi as well, but let's do it for psi dagger. Well, there are no partial derivatives on psi dagger. If you see this guy, oh, and I forgot to explain what is psi bar. Right? Psi bar is psi dagger times gamma 0. Okay, so this you can write down explicitly as psi dagger gamma 0 I partial slash minus m, all acting on psi. So when we come back to what I was saying, so there is no derivatives. There are no derivatives acting on psi dagger. All the derivatives are acting on psi. So this term is immediately 0, and therefore 0 equals to the derivative of the Lagrangian with respect to psi dagger, which is just basically gamma 0 I d slash minus m acting on psi. And gamma 0 is invertible, so I can just multiply both sides by gamma 0, and this will go to 1. When I multiply both sides by gamma 0. And that, of course, is just nothing but the Dirac equation. So I claim that if you do the same thing for psi, now that's a derivative, okay? But if you do the same for psi, I claim you will also get the Dirac equation. Maybe the complex conjugate of it, but you will get the same thing. Okay, so maybe I should make it a homework problem to make you guys. It's just a few steps of manipulating the gamma matrices, but you will get when you plug this in, plug the Lagrangian into this equation, you get exactly the same answer. Right? So it's not independent really. The end results are not independent, even though before you vary, or rather when you vary them, you can treat this, the psi and psi dagger as independent variables, but at the end of the day, they do give you the same, answer. Okay. But now we have the Lagrangian, so we can now ask what is the Hamiltonian. So, remember that firstly we have to introduce the momentum conjugate to psi. Okay? And so psi is just nothing but dl d psi dot. Okay? And so in this case, it might be good to remind ourselves that we can split up the psi slash into the following, right? I gamma 0 partial 0 plus I gamma j partial j minus m psi. Okay, just to be able to see where the psi dot is. It comes from this term here. Psi dot acting on gamma is right here. So therefore, when I take the derivative of the Lagrangian with respect to psi dot, I'm just taking the derivative of this guy, which means I get psi bar I gamma 0, and then what was psi dot now goes to 1, because I took a derivative. But let's expand this out. Remember, we just defined psi bar to be psi dagger I from here, psi dagger gamma 0. That was psi bar. And then we have gamma 0 from here. Now let's refer to our Clifford algebra. Okay, so Clifford tells us gamma 0 plus gamma 0 is twice of eta 0, 0. Okay, that's from the Clifford algebra. Twice because of the anti-commutation. So therefore, gamma 0 squared is actually 1. Or rather the identity matrix. I like to write 1. It's a 4 by 4 matrix, but I write 1 just to indicate it's the identity matrix. So therefore, actually, this is 1. Okay, this is just identity, and therefore it's just I psi dagger. Pi, the conjugate momentum, is just I psi dagger. And so it's now not difficult to construct the Hamiltonian density. Hamiltonian density, remember, is P pi times psi dot, and then minus, right, px dot or pq dot minus L, which is now this fellow over here. So let's write it out like that. Psi dagger gamma 0, and then I gamma 0 partial 0 plus I gamma j partial j minus m psi. Again, I'm splitting it up because of the asymmetry, right? That's always what happens when you do Hamiltonian dynamics. There's a side dot here, and I suspect it's going to cancel out something here, so I want to split up into time and space derivatives. So this is pi. Actually, I times psi dagger is pi. So, and in fact, there is an I here. So there's I psi dagger, which is pi, and then remember that gamma 0 is identity, and then there's psi dot here. Okay, so this term, as I suspected, will cancel out this term. Okay, and so what we're left with is the following Hamiltonian. Let me write this as pi. So I get, in fact, let me write it as the following I pi. Why is it I pi? Because pi contains an I. So if I add an I here, it will be minus sign, which is this minus sign, and then gamma 0, and then I gamma j partial j minus m psi. And that is the Hamiltonian density for our Dirac fermion. Our Dirac fermion. So that's the Hamiltonian. And now we want to ask ourselves, can we make a sensible quantum field theory from this? And if you are used to quantum mechanics, you will say, okay, well, let's do the same thing as we did for bosons, right? X comma P in quantum mechanics is I H bar. In our natural units is 1, I. X comma P is just I. So you might think, let's try the same for fermions. I wouldn't be saying this if there's no trouble, right? Probably if you can read people, you can probably tell that I'm saying something, I'm saying this because we will run into trouble, but let me write it down anyway. Okay, so remember in quantum mechanics, we say X commutated with P is IH bar, which is I in our natural units. So in the bosonic case, bosonic / scalar case, we have in fact successfully impose what we call the equal time commutation relation, right? Phi of x comma t, meaning at a particular space-time location, commutated with this conjugate momentum at the same time, but different spatial locations, will give you the analog of identity. Analog of identity here, because it's a field, is delta function. Okay. So now you might think, well, Dirac. Let me put a question mark. Maybe let's do the same thing. Psi of t at x. Let's try to commute it with pi of t at y. Okay, and then let's say that, oh wow, it's going to give me I times identity, right? So I should mention, this is a 4-component, Okay, so what we're about to discover, maybe as my usual practice, I give everything away. Right? I'm a boring guy. I can't lie. I can't be a good actor either. You know, I just give everything away, and life is too boring, man. Anyway, yeah. So let me tell you what's going to happen. So we're going to run into trouble, and what we're going to end up with is we're going to discover that both the bosonic rules of quantization using commutators is going to fail. And we're going to end up doing, so what the actual rules is actually the anti-commutation relations. Okay. Psi of t of x needs to be anti-commuted with pi of t comma y, and that guy will give you I times delta function. Okay. That's the correct thing to do. And let me tell you what's going to happen first. To just explain the conceptual thing before we go to the heavy technical analysis. What's going to happen is that you can quantize this, okay, until you try to compute the Hamiltonian. So the rules will go through, and what you discover is again you have a set of raising and lowering operators, except now psi is complex, so you actually have two distinct pairs. Whereas when we did phi 4 theory, scalar theory, we only had one pair, because A and A dagger, because it was real. But now these guys are complex, and so we need to now allow for A dagger, and then B dagger. And it all goes through. You can impose the corresponding Fourier space relations for the psi, A dagger, B dagger. They commute with each other if they're not. If A will commute with A, B will commute with B. But A dagger and A will give you delta functions, and B dagger will give you delta functions. Until all that will go through, as we did for the scalar case, until you compute this guy. And what you will then discover is that if you use commutation relations, H will have no lower bound on energy. Okay? So this is a discussion that you can find in Peskin and Schroeder, but I think it's important. So I'm going to try to reproduce at least a good part of it. And so we come to the very important conclusion that for some strange, very unintuitive reason, when you take the Dirac equation and quantize them in the usual rules of quantum mechanics, it just fails. It gives you an answer that is not sensible. Okay, so again, let me, I think I've said this before, let me explain why is it not okay to have a Hamiltonian that does not have a lower bound on energy. Right? If the particle does not interact with anything, maybe it's okay. But we know that there's at least gravity in our universe. So it's not really possible for a particle not to interact with anything. It needs to at least interact with gravity. Right? So this scenario is not even possible in our real world. As far as we can tell, right? So maybe someday we'll find some particle that doesn't interact with gravity. That would actually violate gravity, where the rules of equivalence principle, and actually just the fact that we live in a closed space-time, that would really throw things off quite a bit. But so as far as we can tell, everything has to interact with gravity. So that scenario is out. But so what happens is that if this particle has no lower bound for its energy, then Elon Musk is out of business, right? He wants to create all these solar panels and so on. Well, all I have to do is now get these particles to absorb as much energy as possible. And because I have the total energy is still conserved, if I start with zero energy, I can just impart more and more energy to these guys. Absorb more and more energy, the other way around. Absorb more and more energy from these guys, and they will just keep lowering the energy to no end. There's no bound to it, right? So all I have to do is just keep absorbing more and more energy from these guys. And I don't need the sun. Who cares about the sun anymore? Who cares about nuclear fusion anymore? Right? I can just keep absorbing, and then I've solved the humanity's energy problem forever, right? And so obviously we have not seen any such thing happening in nature before, and therefore, actually, quantum mechanically, you will create a huge instability, right? If your Hamiltonian is unbounded and it really exists in nature, this would create a huge instability once this particle is allowed to interact with other particles. So basically it's impossible, right? As far as we can tell. Not possible at all. And so therefore, the much more sensible, in this situation, much more sensible option is to say that this way of quantizing the fermion is a no-go. You can't do it. Right? Otherwise you can make your electron absorb as much energy as it can, and like I said, who needs the sun anymore? Right? No, who cares? I mean, we can give the electron as much energy as we want, and just produce as much energy in return. Anyway, so what we then discover is that one way out of this is to impose these rules instead, anti-commutation relations. And one of the kind of deep consequence of this is that from this rule, that instead of commutation relations, when we impose anti-commutation relations, we discover Fermi statistics. So you produce Fermi statistics, Fermi Dirac. Sometimes it's called Dirac. I don't know if Dirac actually worked on the statistical part of it, but Fermi Dirac, and this is also what gives you what in quantum mechanics we call the Pauli exclusion principle. Okay. The stability of matter, in fact, why is it that this table doesn't just collapse to its ground state? Right? In principle, all particles can just, it's quantum anyway, right? They can just pile on top of each other and just relax and chill. I mean, what's wrong with that? Well, you can. If it's a fermionic particle, it cannot. Because they cannot all occupy the same quantum state. When you learn quantum mechanics, this statement was asserted, just as a given. But this is one of the deep consequences of doing quantum field theory. Relativity, which is what gave us the Dirac equation in the first place, this guy, relativity plus quantum mechanics gives you this Fermi-Dirac statistics, and as a result, the stability of matter as we know it. So these are very, very non-trivial consequences, but comes out from this very unintuitive dilemma that we hit when we try to quantize fermions, right? So I think we're going to take a break first, but let's after the break begin to actually work through some of this and see for ourselves how this is going to work out. Any questions for me before we take a 10-minute break? No? Okay. See you guys in 10 minutes. If you have managed to solve the homework problem, you will discover that you can start from the rest frame and boost both the energy, positive energy, and negative energy solutions. The positive energy and negative energy solutions, and through boosting from rest frame, you will discover the two sets of solutions, which now I'm going to call U and V. Right? So U of P, which will depend on spin, is given by the following. In your homework, you discover is the top component is written by sigma dot P, acting on a spinner, which I'm going to call zeta of S. So this is two components. So that's why I'm allowed to have an additional label to label the basis for this, which basis I am referring to for this two component object. So either X is 1 or 2, or you can call it plus or minus if you like. But let's just call, maybe I'll do that in fact. So plus or minus if you like. You just need two independent labels, and then for you, the independent, the second component is plus sigma bar dot P zeta S. Okay, and then for the, so this is the positive energy, and then for the negative energy solution, you have the same zeta, but now you have sigma dot P, but now a minus sigma bar dot P in the denominator. Okay. So and this is now the negative energy solution, negative positive energy. Okay. And so in momentum space, if you now write your direct equation using these solutions, you will discover the following. Right? So in momentum space, you will discover that minus I, so what it means is going minus I partial slash minus M, now acting on, for example, U P of S, to put it in a space-time form, you need to multiply it by, of course, the exponential. Right? That's what we mean by a complete basis. It's summed over the general solution will be summed over all momentum modes. But as far as this guy is concerned, this is now becoming P slash minus M acting on UP of S is now equal to 0. Right? So this is now basically the momentum space direct equation. And likewise for the negative energy solutions, you have partial I partial slash minus M now acting on VPS, now is negative energy, so the minus becomes plus IP dot X equal to 0, and the partial derivative acting on the exponential now will give you a minus P instead of plus P. But so you got minus P slash plus M acting on VPS equals to 0. But of course the minus just cancels out, so you can erase this minus sign. Okay, so again, this will give you minus P slash instead of plus P slash. And that's why you get P slash plus M. Finally it connects. Okay, let's see. So with this reminder in place, we can now build the general solution, which then we can quantize. Right? So that's the strategy that we did for the scalar field. And so, let's try to do the same for the scalar field. So we now have our usual integral over k. And then again, our usual normalization, which is 1 over square root of 2ek. So E is always the positive energy, k squared plus m squared. And now, because we have a spinner in the solution, we need to sum over the basis. Right? So we'll always have to sum over the basis spinners. And then we will have our solutions, up of s, e to the minus k dot x in the exponential. And then we have the negative energy solutions, which is v k of s, e to the plus ik dot x. Okay. And then the coefficients, so if this were a classical field solution, then we will superpose them with arbitrary coefficients, which can be momentum dependent. But now, because we're doing quantum field theory, this becomes an operator. Okay, so we've already kind of started doing it by computing the Hamiltonian and so on, but just to remind ourselves, this is now an operator. So therefore, now we will have A, the operator associated with the positive energy particle. And because it has a spin label, we also need to give it a spin label to the creation to the A. And this guy, I'm going to call it BKS dagger. Okay, for as a convention, because that's the ultimate form is going to take. But at this level, we'll realize later on that. Good. Okay. So good. Okay. So at this level, it doesn't matter whether I call it B or B dagger. But ultimately, I want to call it B dagger. So may as well start with the convention that is going to end up being what I'm going to use. So what I'm going to do is I'm going to, in fact, work out and try to impose the commutation relation psi tx pi ty. Okay, actually let me call it x prime just to help my notation. Commutator for now. Okay, and pi we have discovered is in fact simply I times psi dagger. And this is all supposed to give me I times delta function. In this case, I'm doing three dimension space. The form of the Dirac equation that I'm using does depend quite heavily on the fact that it's 3 plus 1 dimensions. So in the scalar case, I could put d there, but now I do need to make sure that this is 3-dimensional, and that's why this integral is 3-dimensional. So what I'm really going to compute is the commutator of psi and psi dagger, and I just want it to be a delta function. So let's do it. So the commutator of psi t x psi dagger t x prime is going to be, I now have a double integral, one for psi, which I'm going to call k, and then the other one for psi dagger, which I'm going to call k prime. That's why I like to call this x prime. Okay, and so now I'll have 1 over square root of 2e k, and then the other one is square root 2e k prime, and then I have a commutator between these two guys, right? So let me also not forget that I have now a double spin sum, s and s prime, and now commutator of a k s u k s e to the minus I k dot x plus b k s dagger v k s e to the plus I k dot x commutator with the dagger. So it's now a k prime s prime dagger. Now I have a u k s u prime dagger. It's been a while since I complained about whiteboards, isn't it, right? See, it always gets fainter and fainter and fainter. Who invented this stuff? Who invented this stuff? Really, man. I need my money back. All the inconveniences and the psychological pain. You know, what is this? You know, oh man, this. And everyone is using it. Okay, anyway. Maybe I need to switch careers and invent things that people will complain about all the time and still make my money, right? Why am I a physicist? Okay, anyway. E to the plus I k prime dot x prime, and then plus b, because I started with a b dagger, so when I take a dagger now it becomes b, k prime s prime, and then v k prime s prime dagger e to the minus I k prime dot x prime. Okay. So because we are running a little bit late, I'm going to just tell you what are the key steps, okay, and we'll see how it's going to work out. So at this level, as I've already advertised, it will work out. And so how will it work out? I will simply be able to impose commutation relations between the A and A daggers and B daggers. That's the key point. So let me just say, it will give delta function of x minus x prime if we do the following. Okay, so the first thing is familiar, which is AKS, and then if you impose the commutation relation between AKS with AK prime S prime dagger, and because now there's an extra spin index, firstly I need a connected delta between them, because the spinner indices can always be chosen, or the basis can be chosen so that they're always orthonormal, right? So assuming I have chosen such a